Hello, class. Today's video is going to be over section 4.1, Hindu, Arabic, and early positional system number systems. And so, yes, we are moving on from chapter 3 of the truth tables. For those of you that like the truth tables and are disappointed we're not doing more of it, we had like a whole other 4 or 5 sections we could have done, but I think we kind of already did our logic with chapter 2 in the Venn diagram stuff. So we're moving on to a new topic. All right, so chapter 4 is about number systems. It is some sort of historical background on this. Many years ago, when the learning objectives for the survey course are being decided, there were a lot of education majors. So chapter 4 is specifically addressed for education majors, but we're all going to cover it. So we're going to cover 4 sections in chapter 4. The first, 4.1 through 4.4. The 4.1 and 4.4 for me are sort of like historical aspects of our number system, and so you'll gain a little bit of insight on. We're going to talk today about the Babylonian number system a little bit. We'll get into 4.4. We'll talk a little bit about Egyptian and Roman numerals. So you'll kind of get a feel for number systems other than our own, which I think is never hurts. And then in 4.2 and 4.3, we're going to do some like converting between number bases. Like our decimal system is base 10, but there's base 2, binary, there's base 8, there's, base 20, base 60. There's a lot of other bases other than 10 that we can use for numbers. And so we'll kind of explore how to do that and basically how to do some basic adding, subtracting. Right, but that's for other videos. So for today, we're going to do 4.1 and we'll talk about our number system and the Babylonian number system. And as always, I'm taking this from the lecture notes from that I posted on Blackboard. I don't have a separate definition page and example page like I did with the true tables, because I think with this, we don't really need it. It flows better. So let's just jump into our notes. Okay. So for the Hindu Arabic system, the reason that we call our number system the Hindu Arabic system, in case you may not have heard that before, is it really kind of the history of where our base 10 number system came from. Like in India and Persia, that area is where the notation that we're using was developed, and that's where like where the core of where it started. And then if you look over, if you've ever taken an ancient history class and kind of saw like the flow of population from between Europe and Asia, the Arabs moved into Europe after coming from Asia, and so as they came, they brought the Hindu number system with them, and plus on top of the adjustments and advances they made to it. So that's why we call our number system the Hindu-Arabic number system. It just history of our species a little bit. Okay, so what is our system based on? It's based on powers of 10. And the reason it's on 10 is as a species, we have 10 fingers. And so, if we had 8 fingers, and we'd be working on a base 8 system, and so on. But because of our fingers, we're focusing on powers of 10. And what do I mean by powers of 10? Well, 10 to the third, 10 to the second, 10 to the first, and our discussion of scientific notation actually kind of helped us prep for this, because now we know that 10 to the 0, by definition, that's 1. And then we also talked a little bit on scientific notation that if we have negative exponents on our powers of 10, then we're dealing with decimals, so that still applies. Now, and if you might have noticed that it was called positional number system, it is because once we started expanding it, so the position of the number tells us the value. We're much more used. I don't know about you. I don't ever call it positional value system. We call it place value. So I'm going to use place value very often when maybe the more proper term might be positional value. But just I use this interchangeably. So when you see positional systems, just think of place value. Basically means the same thing. And what are we, why is this important? Well, here, for example, why is we know at this point in our lives that 732 is not equal to 237 because that's 732, whereas this is 237. How do we know that? Because that 7 is in the third position to the left. So that is the 100 spot, the 10 spot, and the 1 spot. So this has 700s, this has 200s. At this stage in our lives, we've used it so often you may not think about it. But that's what we're talking about with positional value system and its powers of 10. All right, so something that we're going to do a lot in 4.1 is something we call expanded form. And this will also help us when this is kind of what we need to be able to do when we're changing between bases in 4.2 and 4.3. So when we write a number in expanded form, so let's look at the 732. Well, what does the 7 mean? What does the 3 mean? What does the 2 mean? Well, we know the 7 is 700. So we can write that as 7 times. Now, we could write it as 100. But if we're talking about powers of 10, 100 is 10 squared. And then that 3 is 30, which means 3 times 10. Or if we do it in exponent form, 3 times 10 to the first. And then the 2, that's 2 ones. So 2 times 1. Or 10 to the 0 also means 1. So the way the book does this, they prefer the expanded form using the exponents. So, and actually on the 1, they're kind of inconsistent. So the book preferred way, or in the homework, the preferred way would be to use exponents for everything except the 1's place value, and then they just use 1. Now I have experimented in 4.1. They will accept 10 squared or 100, or they'll accept 10 to the first or 10. So in the examples, I'll try to use the exponents, but honestly, for me, I think Rollins, it's probably quicker to write 100 than it is to get, use the exponent keys and get 10 squared. A couple other things. Do not use X's. The letter X when you're writing this in expanded form. MATLAB will count it wrong. So when you do the button palette, when you click on the answer box, they do have the multiplication symbol. On your keyboard, if you do Shift-8 and the star, it'll also get you the multiplication symbol. But you'll definitely get it wrong if you use 7x, times 100. What else? Yeah, so don't skip your zeros. MATLAB may or may not accept this. Sometimes MATLAB is picky. So if we have a number like 702 rather than 732, that 0 still tells us there's 0 tens. So to be fully correct, we need that 0 there. Don't just assume 0 is nothing. MATLAB may let you get away with not putting it in there. It sort of depends on who coded the question. The other thing is, I did mention that MATLAB, when we're doing the expanded form, will accept the written out numbers, not necessarily, you don't always have to put it in exponential form. When we get into 4.2 and do this for other bases, I haven't checked yet if they'll accept that. So it doesn't hurt, like for in base 6, and you want a 6 to the third. It also, but 6 to the third is 216. I don't know if MATLAB would accept the 216. Whereas, 10 to the third is 1,000. I know it would accept 1,000. Okay. So when in doubt, you can always look at the answer in the examples, but we're doing other number systems. I'm going to try to be more consistent and always use exponential form. But if we're doing power of 10, sometimes I will, go over. It's not so bad when you're writing it by hand, but, when you're trying to do it on the keyboard, you have to, select the, like that 10 to the, or not even, might even be 10, you'll have that box, where you have to put the base and the exponent, and it just takes longer if you're typing it. All right. And the other thing I will point out, scientific notation will help. Most of the time, we're going to be dealing with whole numbers bigger than 1. So the vast majority of the time, we're dealing with positive exponents. In the homework, you're going to have, there's 1 or 2 decimal questions. And so you're dealing with decimals when you have those negative exponents. So just kind of keep that in the back of your mind. That will pop up a couple of times, but most of the time, we're dealing with large positive numbers. Okay. So let's just jump into some problems. And once you get the hang of this, it may seem like a little bit of overkill in 4.1, but I want to make sure that everybody's comfortable with expanded form in base 10 before we get into 4.2 and need that expanded form in other bases. So write 72 in expanded form. Well, 72 means 70 plus 2. So that's the first part of the expansion. And so now we have to write it in powers of 10. So we can't write 70. What we need is 70 times 10. Oh, I don't want to use the x. Times 10 plus 2 times 1, or 70 times 10 to the first plus 2 times 1. So this would be like the fully correct, or like maybe the best answer. This would be acceptable. And you may think you don't need the 1, but we are doing powers of 10 and when we're expanding this. And so, that is 1 is one of our powers of 10. It's when we have a power of 2. Let's do a couple more of these. All right. So 1452. So that's 1,000 plus 400 plus 50 plus 2. And you don't necessarily have to write this intermediate step. I think for the notes, it's helpful if I have this and go back and look at it. And so now we have to write this in. So we expanded it on place value. Now we need to write it in exponential form. So that is 1 times 1,000. And so 1,000 is 10 to the third. And then 400 is 4 times 100. 100 is 10 squared. And then 50 is 5 times 10. And 10 is 10 to the first. Yeah, so 1,000, 10 to the second is 100, 10 to the first is 10, and so on. And then 2 is 2 times 1. So that's what they're looking for in expanded form. And you need all of that. Again, don't use x's. Use your multiplication with the Shift 8 on the keyboard or the multiplication symbol from the button palette below your answer. This would also be acceptable if you actually wrote out 1,000 and wrote out 100 and wrote out 10. MATLAB will accept that. At least the couple examples I tried it does accept it. All right, so let's jump down to number 6. So we have 60,803. So that is 60,000 plus 0 plus 800 plus 0 plus 3. Okay, so and the reason I'm putting the zeros there, that is the thousands spot. And so there are 0 thousands. And there are 0 tens. All right, so now let's put it in exponential form. So 60,000 is 6 times, well, 10 to what power? You have 1, 2, 3, 4 zeros, so 10 to the 4th. Plus, how many thousands do we have? We have 0, so we do 0. Now 1,000 is 10 to the third. And then 800 is going to be 8 times 100. 100 is 10 squared. And then we have 0 tens. It'd be 10 to the first plus 3 times 1. So that is the most proper form of this answer written out in expanded form. Now, I did not check if MATLAB would accept if you left out the zeros in the expanded form, because that is still just 0. It's better to put it and not need it than the other way around. And again, they should also accept if you do 60 times 10,000 and 0 times 1,000 and then 8 times 100 rather than putting in exponential form. Well, like I said, at least for base 10, it does accept that. All right. So as long as you know your place values, that's basically what we're doing is we're writing this out on place values. And instead of writing out in word form what the place value is, we're writing it out in exponential form with powers of 10. All right, so that is starting with the standard number, going expanded form. Now we go backwards. Yep. So express each number as express the expanded form as a Hindu Arabic number. So when it says Hindu Arabic numeral, those are our normal. All right, so when you have 40 times 10 to the first plus 2 times 1, well, that 40 means 10. So that gives us 40. 2 times 1 is 2. And so that's just 42. So they're basically saying, can you take the expanded form, go backwards, and give us the original number? So depending on how comfortable with it is you may be able to do this one step. It may take 2 steps. It just depends on where you're at. So 1 times 10 to the second, that's 100. 50 times 10, or 5 times 10 is 50. 7 times 1 is 7. 1, 5, 7. Okay. Or you could, notice that you're not missing any exponents. So this is 10 to the 0. So you have your 0, your tens, and then your hundreds. So you can just work backwards. 7, 5, 1. You have to be careful with that shortcut. If you're missing any exponents, if you're missing an exponent, then that means you have the 0. You have to watch out for. All right, so go ahead and do next couple, see what you get. We have 10 to the fifth, that's 5 zeros. Yeah, we're dealing with whole number exponents. That exponent tells you how many zeros you have. Okay. So number 9 is 992,377. And again, the shortcut is, you have your ones, then your tens, then your hundreds, 3, 4, 5. So you're not missing any of your exponents. So you can just work backwards. 7, 7, 3, 2, 9, 9. Okay. And then after that one, 10 is probably pretty quick. So what do we have? We have 7,000 plus 0 plus 0 plus 1, which gives us 7,001. Right. So those zeros are important. Those zeros are important because those are hold placeholders for a specific place value. In this case, the hundreds had to have 0 and the tens had to have 0. Now, what about number 11? 9 times 10 to the 8th plus 9 times 10 to the 3rd plus 6 times 1. All right, so we are definitely missing several terms. So there are several exponents. Okay. Now, if you're not for sure, like trying to do this all at once, then go ahead and write it out. So 10 to the 8th, 9 times 10 to the 8th means 8 zeros. 8. Here's another way to do it. So 9 times 10 to the 3rd means 3 zeros. So 0, 0, 0, 9. And then 6 times 1 is 6. So this is, before I was writing it out horizontally, something like this where I'm missing terms, and writing it vertically helps you line it up. We got 6, 0, 0, and then that 10 to the 3rd is our thousands spot. And then that 10 to the 8th is our, what is that, millions, billions, 10 billions, 100 billions. So 900, not in the billions, I'm in the thousands. So thousands, millions, sorry. So 900 million, 9,006. Yeah. Like I said, once you get the expanded form is something that in the back of the mind, this is what I think we do, especially like when you're adding and subtracting numbers. A lot of times we'll do that in our brain in expanded form and maybe not realize it. And adding tens with tens and so on. So this is something that now we're just writing it out explicitly. All right. So how about the next one? If n is a natural number, then 10 to the negative n is 1 over 10 to the n. So this is, we've talked about how to deal with negative exponents a little bit in test 2. Rather than think of it this way, this is why I said scientific notation is handy. So when you see those negative exponents, we know we're dealing with decimal numbers. Now, the one thing, sort of the quick thing here is like if you have a positive exponent on a power of 10, that tells you how many zeros, and then your digit is in front of it. When you're dealing with negative exponents, that negative exponent tells you the position of that front digit. Because that is, because 10 to the negative 1 is 1 over 10, that's a tenth. So that is actually 3/10. So the way that I would do this, so that is the first spot past to the right of the decimal is a 3. The second spot past the decimal is a 2. The third spot past the decimal is a 6. Okay, so when you're dealing with decimal negative exponent notation, the exponent tells you which place that digit goes into. It's not the number of zeros in front of it, it's the place where it actually is. So that comes in handy when you're dealing with something like this that has some missing terms. So these are all negative exponents, so we're dealing with just a decimal. So that 2 to the negative 1 says that 2 is in the first decimal place. Now there is no negative 2 exponent. That means we have a 0 in the second decimal place. In the third decimal place, that 5 negative 3, we have 5. There is no 10 to the negative 4 digit, so that tells us it's 0. So then 2 times negative 5 says on the fifth spot, we have a 2. 1, 2, 3, 4, 5. Now there is no negative 6 exponent in this problem, so that tells us the sixth place is 0. And then 3 times 10 to the negative 7th says 3 is the seventh place at 1, 2, 3, 4, 5, 6, 7. Okay. So if you don't put those zeros in there, then you would have what? Then you'd have 0.2523. And so that, that 3 is definitely not in the 7 spot. And if you think about this in terms of scientific notation, 3 times 10 to the negative 7 is you move the decimal over once, and then you got to move it 6 more places. So there's, there's once, and then 2, 3, 1, 2, 3, 4, 5, 6, 7. So that's where, scientific notation can help us with this. All right, and like I said, in the homework, there's only 1 or 2 decimal problems. Everything else that we're dealing with is going to be whole numbers. All right, so that is our number system. That's, I tend to think it's the decimal number system, but the official name is the Hindu Arabic system. Okay, what about other number systems? So in the history of math, Babylonian system is one that gets talked about a lot because the Babylonian number system is actually based on 60. Well, why 60? Well, whoever was in charge of developing their numbers over time, one of the nice things about 60, it divides by a lot of numbers, by 5, by 10, by 12, by 15. There's a lot of divisibility possibilities with 60. That's sort of the theory. None of us were actually alive back then, so we don't know exactly all of the thought process into that. But they don't count up to just 10; they count up to 60 before they start over. And why are we talking about the Babylonian system? Well, our time is still based on the Babylonian time system. That's why there's 60 seconds in a minute, 60 minutes in an hour. Why there's 24 hours in a day, then that's beyond what we're talking about here, but that's our minutes and our seconds are definitely based on Babylonian number system. Okay, so one of our digits 1 through or 0 through 9, that's not how math has always been done. Very many civilizations have had different symbols other than our digits that we like. And so for the Babylonian number system, and honestly, I don't know if there's more, but I do know these are the key. And when you're doing the homework, for any of these other number systems, these symbols are going to be part of the problem. I think there might be one homework on the Babylonian system where that's not here, but it's in all the rest of them. And I'll make sure on the test, that one problem won't be on the test. So on the test, if we're dealing with Babylonian system or the Egyptian or the Roman numeral system in 4.4, the symbols will be stated in the problem. So you don't have to have those memorized or on your one page of notes that you get. Okay, so a V character is 1. The less than symbol is going to be 10. And so when when we talked about our number system being based on powers of 10, the Babylonian system is based on powers of 60. So the ones position is still to the 0 power, because anything to the 0 power other than 0 is 1. Then where we have our tens spot, theirs is basically a 60 spot, because 60 to the first is 60. Now where we have our hundreds, which is 10 squared, their equivalent of that would be 60 squared, which is 3,600. Our thousand spot is 10 to the third. Their equivalent of the thousand spot is 60 to the third, which ends up being 216,000. And so on. For our 10,000s, which would be 10 to the fourth, their equivalent would be 60 to the fourth. And so you can see their numbers go really big, really quick when you start talking about powers of 10. They probably didn't really need numbers that big, but that will come in more into play, particularly when we get into 4.2. All right, so what are we going to do with this? Basically, we're going to give you some experience in reading a new number system. All right, so here's what some homework is going to look like. So again, B stands for 1, less than stands for 10. We're going to write Babylonian number as in Hindu Arabic in our number system. One of the things to watch out for is look for spaces. You know how we use commas for every 3 to kind of help us separate them? The way they separate their place value is with spaces in the number. So like if you look here, there is no big gap between them. So this is all sort of like in the ones place value. On this one, we have 1 space. So this is the ones equivalent place value, and this is like the 60s place value. Here we have 2 spaces. So this is the ones place value. This is the 60s place value. This is the 60 squared place value. So like for us, that would be like the ones, the tens, and the hundreds. Remember, they're dealing with base powers of 60, not powers of 10. So how do we read this? Right, so we have less than VVV. And so the less thans are tens. So that's 10 plus 10. So that part of it is 20. And then the V's are 1. So we have 1 plus 1 plus 1. So that part is 3. So that Babylonian number right there is equivalent to 23 in our number system. All right. That was pretty straightforward because we didn't have to worry about these different powers of 60. Now we get to, all right, what do we have here? So we have the space between the first 3 and the second 2. So let me get different colors here. Where's purple? All right. So the right side, that is the ones place value. The left side, for us, it would be the tens. But remember, Babylonians are base 60. So this is 60 to the 60 to the first place value. What we need to do is treat these each separately and then do expanded form. So let's start with the VV because that's the ones. So VV, remember the V stands for 1. So that's 1 plus 1. So that's 2. That's 2 ones. That's the ones place value. Now for the less than V, remember the less thans stand for 10. That's 10 plus 10 plus 1, which is 21. This is not 21 ones. This is 21 of 60 to the first. What does that mean? Well, think about this in terms of expanded form. So we have 21 times, well, that is in the 60 to the first place value, plus our position, plus 2 in the ones place value. So that is 21 times 60 plus 2. Now, I don't know about you, but I'm going to grab a calculator. 21 times 60 is 1260 plus 2, which is 1262. Right, so that is what, and again, I don't know I don't know the names that they use for this. I should probably look that up. But that's less than V space VV in Babylonian translates to 1,262. All right. Didn't realize when you started watching this video that you're going to be dealing in a language that's what, 3,000 years old, maybe? We're talking in an ancient tongue here. Okay, so 17. Now we have two spaces. So we need to know the positional value of each one of these. And so this is the ones. Now go to the left. This, we're base 60 because we're in Babylonian. So 60 to the first. The next one over, now it's going to be 60 squared. If this was our number system, it'd be the ones, the tens, and the hundreds. But remember, for Babylonians, the tens is 60 to the first. The equivalent of the hundreds is 60 squared instead of 10 squared. Okay. So now for each one of these, we need to figure out what it means. Let's start with the 60 squared place. So V. Remember, V stands for 1, plus 1, plus 1, plus 1. So that's 3. That's in the 60 squared place value. So we're going to multiply that times 60 squared. I'll come back and do the arithmetic on that in a bit. The middle term is less than VV. The less than stands for 10. V's stand for 1. So that gives us 12. This is in the 1 or the 60 to the first place value or position. So it's going to be 12 times 60 to the first. And then the third one, it's VVV, which we've already done that. That's 1 plus 1 plus 1, which is 3. That position is the ones position, so it's 3 times 1. Okay. So this is, so to translate this Babylonian number into our current number system, 1, you need to be able to know what the V's and the less thans mean, and 2, which position is it? And remember, just like our number system, it starts on the right with the ones, and as you go left, it goes 10 to the first, 10 to the second, 10 to the third. Babylonian system starts at the ones, and then as you go to the left, it's 60 to the first, 60 to the second. And I'm not doing any examples here today that have more than 60 to the second. In the homework, you might have, if you have a third space, then you might have a 60 cubed. All right, now let's finish this problem. We want the actual number in our number system. So now 3 times 60 squared. And I just did the whole number at once. So 10,800. 12 times 60 is 720. And then 3 times 1 is 3. Add those all together. So 11,523. So translating this several thousand-year-old numbers into our number system, VVV space less than VV space VVV is 11,523. All right. It's sort of like truth tables is like you kind of go step by step. As long as this is one reason why the homework kind of had you do maybe more expanded form than they thought you might have needed, is because it becomes helpful once we start doing this in other bases. So we can kind of do it without thinking about it sometimes for base 10. You need to think about it when our base is not 10. Okay. Now here's where you have to be careful and read the instructions. So in these problems, it said write the Babylonian number as a Hindu Arabic number. So that's why we were done when we had the 23, we had the 1262, 1152, because that's a Hindu Arabic number. That's a normal number. Look at the instructions now. Express the result of the addition as a Hindu Arabic number in expanded form. All right, so Hindu Arabic number in expanded form. So they don't want this answer or this answer. They want to take this answer, and then we got to put it in expanded form. So if you miss that in instructions, then that's like that's why a lot of people will miss these problems, because they stop too soon. Okay. All right, so let's look at 18. Now I'm going to cheat. All right, actually, I cheated when I wrote this problem. If you notice, isn't 17 and 18, I can't get them on the camera at the same time. Those are the same Babylonian number system. So VVV, VVV, less than VV, and then 3Vs, less than VV, and then 3Vs. So since we've done step one. So step one, converted to Hindu Arabic system. That was number 17. We already know that's 11,523. So I cheated. Okay. So we have to do step two now, go to expanded form. Expanded form, now we're back in our base 10 system. So this is 10,000 plus 1,000 plus 500 plus 20 plus 3, which is, so 10,000 is 1 times 10. You can either say 10,000 or what's the exponent? Well, you got 4 zeros, so 10 to the fourth. 1,000 is 1 times 3 zeros, so 10 to the third, plus 500, which is 5 times 100, or 10 to the second, plus 20, which is 2 times 10, or 2 times 10 to the first, plus 3, which is 3 times 1. But really, these two problems are a combination of translating Babylonian to our number system plus expanded form. All right, last example. Okay, so we have two spaces. I think it's really helpful to especially for other number systems, to write out the place value or the position value. So going from right to left, that's the ones. We're in Babylonian, so this is 60 to the first, and then that's 60 to the second. So now we need to convert it to our number system, and then we need to convert it to expanded form. So less than V, less than is 10, V is 1, that's 11. Now that is in the 60 squared position, so we're going to multiply that by 60 squared. Kind of run out of room, so I'll do that arithmetic after I do all the translation. So now we have less than, and then 1, 2, 3, 4, 5 V's. That's 10 plus equals 10 plus 5, so that's 15. Now this is in the 60 to the first position. And then we have 4 less thans, V. So those are tens, so that would be 40 plus 1, which is 41. This is in the ones, so that's times 1. And again, I really wish I could pause and see if there's any questions here, but I can't do that, so I'll just keep going. So now I want to deal with the arithmetic of this. So 11 times 60 squared is 11 times 60 squared is 39,600. 15 times 60 is 900. And 41 times 1 is obviously 41. Now we add all those together. For a final total of 40,541. All right, so that is step one, convert it to Hindu Arabic system. Now we need an expanded form. So 40,000 is 4 times 10,000, which 10,000 is 4 zeros. We have 0 thousands, so plus 0 times 10 to the third, plus 500, which is 5 times 100, or 5 times 10 squared, plus 40, which is 4 times 10, or 10 to the first, plus 1, which is 1 times 1. All right, that is our Babylonian number system, or at least, what we're going to deal with it. Let me get into the homework right quick. See if there's anything else I need to add to this. Or maybe show you how stuff works. Let me show you a couple of problems. I don't think we're going to see anything different here, but just in case. All right, so I'm in the 4.1 homework. I just did a random problem. This is number 9. So express the expanded number as Hindu Arabic number system. And so that's 5 times 10 is 50, plus 4 times 1, that's 54. And that's pretty straightforward. A little bit earlier, it put it in expanded form. So 83 is 80 plus 3. And so then you have to do, 80 times 10, or 8. So you have the multiplication dot down here that you can use, or again, you can use the shift 8. And if you want to do exponents, then you need this box. Oh, I can do 10 first, and then you do that box. Okay, sometimes you got to play around with it. Okay, so there's the 80, and then cursor over, so the cursor's big, plus 3 times 1. So that would be the preferred way to write it. You could do 80 times 10. Let me play around with this just a little bit. So we know that's 572, so that's 5 times 100. So let's try this. 5 times 100 plus 70 is 7 times 10 plus 2. Let me leave off the times 1, see if MATLAB accepts it. See, so it says that's incorrect. So you definitely have to have that times 1 on there, or it will count it wrong. Now okay, so this is 800, so 8 times 100. I want to leave off the 0 to see if MATLAB will take that. 1. Okay, so MATLAB doesn't always use common sense, but on this one, when it had that 0, it didn't force me to write in the 0 tens. The other thing to remember is don't use X. Because it will definitely count that wrong. Because your answer contains the letter X. You think it means multiplication, but MATLAB is interpreting that X as a variable. So do not use X's for multiplication. Either use the multiplication dot from the button palette or the shift 8 start. So let me jump down here further. So like this is, let's see, 12 is, so it looks like in the homework there is only, there's only 1 decimal question in the homework. So when you see those negative exponents, just remember you're dealing with decimals. And we did a couple examples of that in the video. All right, and so this is what I was talking about. So we're in the Babylonian system. They give you what the V and the less than. So you don't have to have it memorized. It's there. Okay. It's not in table form here, but it's still giving it to you. I think there is one. Was there one that may not have it? If that's the case, then you can, like it's at one problem at most. Okay. That is 4.1. As always, if you have any questions, email me. Have a good day.